Auzubillahiminash-shaytanir-rajim. Bismillahir-Rahmanir-Rahim. Hello everyone, welcome back to Material Studio Zone. Today we are going to learn something very exciting and important for materials research. How to calculate STM profile using CASTEP and Material Studio. This is very powerful technique that allows us to see a material at the atomic level, just like having super microscopic eyes that can see individual atom and electrons. Today's lecture is special because we will cover complete STM calculation from beginning to end. And by the end of this lecture, you will know exactly how to set up STM calculation, create beautiful STM images, and analyze results like professional researchers. We'll also look at a real example of pure TI2C to understand how doping change electronic properties. STM stands for Scanning Tunneling Microscopy, and it's one of the most important technique in nanotechnology and material science. It helps us understand how electrons behave on surface, which is crucial for designing better catalysts, electronic devices, and energy storage material. When we combine experimental STM with computational prediction, we can accelerate material discovery significantly. And let's understand STM theory. So before we start the practical calculation, let me explain what STM actually does and why it is so important. Uh, for this, imagine you have an extremely sharp needle, so sharp that it ends in just one atom. This needle can detect electron on a material surface. When we move this needle across the surface, it measures how many electrons are present at each position. The basic principle is simple but powerful. Where there are many electrons, the STM signal is strong, and we see bright spot in our image. Where there are fewer electrons, the signal is weak, and we see dark region. This create a map of electron density across the surface, which tells us about the electronic structure and chemical activity of different atoms. And in our computational approach using CASTEP, we calculate these electron density using quantum mechanics, and the software solves the Schrodinger equation to find where electrons are most likely to be found near the surfaces. This theoretical prediction can then be compared with experimental STM images to validate our understanding of the material. And the beauty of computational STM is that we can predict results before doing expensive experiment. We can also study material that are difficult to synthesize or measure experimentally. And this makes computational STM a powerful tool for material design and discovery. So, before we can calculate STM profile, we need to prepare our system properly. The most important requirement is that you must have a complete geometry optimization of your structure. STM calculation require the atomic position to be fully relaxed and optimized. If your atom are not in their equilibrium position, the STM results. The STM if your STM are not in their equilibrium position, the STM results will not be meaningful. So make sure your surface is clean and represent the system you want to study. If you are studying a dope material like we'll do today, the dopant atoms should be properly substituted in the host lattice. The doping concentration should be realistic and represent what you want to achieve experimentally, and also make sure you have enough disk space, because STM calculation generate a large file containing electronic wave function information. So since we already have perform geometry optimization, and we also perform the STM profile calculations. This is our optimized structure, and now let's start the actual STM calculation steps. First, open your optimized structure in Material Studio. You should see your relaxed atomic position with reasonable bond length and no overlapping atom. Once your structure is ready, and then from module section, open the case tip, open the case tip calculation, and from drop down menu, this will open the case tip calculation dialog, where we will set up our STM calculation. So in the setup tab, the first and most important change is to set the task to energy instead of geometry optimization. So this is crucial because we only need the electronic structure calculation, not another structural relaxation. Since we already have optimized atomic position, we just need CASTEP to calculate the electronic wave function that will use for STM simulation. Now move to the property tab, and this is the most critical step for STM calculation. You must check the box label orbital, and make sure all other properties are unchecked. The orbital option tells CASTEP to save the electronic view function, which are exactly what we need to calculate STM profile. Without this, you cannot generate STM image. So please don't forget this step. And and the electronic tab use the same setting that you use for your geometric optimization. If you are unsure about this setting, the default will you usually work well. So and for k point sampling, use the same grade that give you good convergence in your optimization. Remember that higher k point grade give better accuracy but require more computation time. So and then finally click on the run button to start the calculation. Give your job a descriptive name like STM TI2 or whatever you want. So STM TI2C. So you can easily identify it later. The calculation will typically run faster than geometric optimization because we are only doing single point energy calculation. Since I already performed this calculation, so just skip this, and I will directly open the already calculated file. Yeah, this one. So for this, I already performed the STM calculation. So let's how to create STM images. So after your CASTEP calculation finishes successfully, we can now create the actual STM image. So for this, click on the CASTEP button and select analysis. Analysis from the drop down menu. This open the CASTEP analysis dialog, which contain various post processing tool, and that look for STM profile in the list and click on it to open the STM tools analysis. Yeah, here we have. Okay, and the STM profile dialog, you need to select your CASTEP output file. I see already, which should have a CASTEP extension. Next, set the STM bias voltage. I recommend to starting with +1 electron volt, which probes the unoccupied electronic state above the Fermi level. You can experiment with different bias. We'll use later to see different aspect of the electronic structure. Make sure to uncheck view isosurface on import option for now, as we want to control the visualization manually. So click the import button to yeah, since we already have, so I want to create another one. Click on yes. Okay, so after clicking the import button, this process reads the electronic view function and prepares them for visualization. You might not see any visual changes yet, but the STM data is now available in your structure file. Now come to the exacting part, creating the actual STM image. and find the volume visualization toolbar. And so for this, find the volume visualization toolbar, and the since we have here, and click on the small arrow, and let's set the angle for it. The better one is the third option is better parallel to A and B axis. This create a horizontal slice through your electronic density data, which represent what an STM tape would see when scanning across the surface. The position of this slice is extremely important. So yeah, we already calculated so many. So yeah, okay. Now the position of this slice is extremely important. So select the slice by clicking on it, and look at the properties explorer panel. Find the slice position property and adjust the z coordinate. So set it to about 1 to 2 angstrom above your highest atom. Uh, so since we already have moving tool and material studio. Okay, it should be 1 or 2 angstrom. Or yeah, now it's visual. Okay, so optimizing a STM visualization to create professional looking STM image, we need to optimize the color mapping and visualization setting with your slice selected. So click on the color maps. As we have color maps button to so click on this button to open color mapping dialog. Here you can choose different color scheme depending on your purpose. So for publication quality, I recommend using black and white. uh, a grayscale color scheme. These look professional and research paper and are easy to interpret. So for detail analysis and presentation, the rainbow color scheme is excellent because it show suitable variation in electronic density very clearly. So you can see fine detail that might be missed with a simpler color scheme. The color range is crucial for good contrast. Instead of using the full range from minimum to maximum value, try setting the from value to about 10 to 20% of the maximum, and the two values to about 80 to 90% of the maximum. This eliminates background noise and enhance the important feature in your STM images. Uh, Also, let's set the number of bands to 128 for smooth color transition. This gives professional quality images without visible color steps. You can experiment with different number, but 128 is usually optimal for most purposes. Adjust your view angle to get the best perspective of your image, and a top down view is usually best for seeing the electronic pattern clearly. You might want to make the atom smaller or more transparent, so they don't have the STM slice. The goal is to clearly show the relationship between atomic position and electronic density pattern. So since we perform calculations for STM profile, so let's analyze. Let me now show you how to analyze STM results using real example. Uh, so you see, we perform STM for our TI2C. Yeah, it's a dog TI2C. We also have a show legend option. Okay, so if you see the STM pattern show perfect periodicity and symmetry, reflecting the crystalline structure in Ti2C. All titanium atom appear with similar brightness, indicating a homogeneous electronic environment, and the carbon atom are less visible in the STM image because they contribute less to the electronic density at energy we are probing. And in our example, the maximum electron density reach about 2.92 multiplied 10 to the power minus 1 and arbitrary unit with a dynamic range of about 140 times between the brightest and darkest region. And this gives a good contrast for identify atomic position and electronic features. The uniform distribution tells us that the Ti2C has consistent electronic properties across the surface. And the baseline understanding of this example is essential because it allows us to understand how doping modify the electronic structure, and any changes we see in doped system can be directly attributed to the dopant atom and their effect on the host material. Let me give you some practical tips for STM analysis. First, always start with the well-optimized structure. If your atomic position are not properly relaxed, so the electronic structure will not be meaningful, and your STM image will be unreliable. And when setting up the Okay, and when setting up the calculation, double check that you have enabled the orbital option in the property tabs. This is the most common mistake that prevents STM analysis. Without the orbital information, you cannot generate STM profile. So this step is absolutely critical. And for the STM slice position, experiment with different height above the surface. Real STM experiment are typically performed 1 to 3 angstrom above the surface. Too close, and you will see most the atomic position. For too far, you will lose the fine electronic detail. So better is to start with 1.5 angstrom and adjust as needed. Uh, Also try a different bias voltage to probe different aspect of the electronic structure. Positive bias voltage probe unoccupied state above the Fermi level, while negative bias voltage probe occupied state below the Fermi level. Different bias value can reveal different features and provide complementary information. And for color mapping, the rainbow color scheme is excellent for detailed analysis because it shows suitable variation clearly. However, for publication, grayscale or black-white scheme are more professional and easier to interpret. So let me conclude. So today we have covered a complete journey through STM profile, calculating using CASTEP, and we started with the basic theory, learned how to set up calculation properly, and then we learn create professional STM images and analyze real examples of uh, TI2C or DOW TI2C. And the key takeaway from today's lecture are always ensure proper structure optimization before STM calculation. Also remember to enable orbital calculation in CASTEP, and position your STM slice carefully above the surface, and use properties color appropriate color mapping for a clear visualization. Uh, with this, thank you very much for joining me for this uh, comprehensive class. If this lecture helped you understand STM calculation better, please like the video and subscribe to our channel for more advanced material modeling content. And also, if you have any question, leave your comment. I will answer you. I read every comment and will help you solve any challenge you encounter. In our next video, we'll explore advanced STM technique and how to prepare for publication quality STM figure for research paper. Until then, keep smile, be happy.